This is the third Math 23 video for week 1. We're moving on now from vectors to matrices. And before viewing this video, you should familiarize yourself with subsections 1.4 up through 1.10 of the executive summary. First, let's consider how to create a matrix in R. For our purposes, the most important feature of a matrix is that the first column represents what happens when a linear transformation acts on the first standard basis vector. The second column, what happens when that linear transformation acts on the second standard basis vector, and so on. So the natural way for us to make a matrix is column by column. If the first column has a 2 and a 4 in it, and the second column has a 1 and a 5 in it, the R function cbind will bind them together into a matrix, and you can see the matrix displayed at the bottom with the 2 specified columns. Conveniently, R even reminds us of the names that those columns had when we thought of them as vectors. From time to time, we'll use a matrix to represent a system of linear equations, and in that case, the coefficients in an equation become a row of a matrix. It's also possible in R to make a matrix by binding rows together. So if the top row is 2, 1, and the bottom row is 2, 5, those 2 rows R1 and R2 can be bound together into exactly the same matrix as before. Now the matrix is displayed with names on the rows. If you're feeling a little bit lazier, you can just specify all the entries in the matrix, but you have to tell R quite a bit now. You have to tell it the shape of the matrix. It's a 2 by 2 matrix, and you also have to tell it whether you're filling it in row by row, as I've done in the first of the 2 lines, or column by column, going 2, 4, 1, 5. Either way will work. In fact, everyone ends up getting lazy and uses the shortest possible way of doing this. The shortest possible way of doing this is you concatenate all the entries in the matrix into a single vector, going down the columns one at a time, and then you specify how many columns there are in the matrix. So this says I want to make a matrix A whose entries going down the columns are 2, 4, 1, 5, and this matrix has 2 rows and therefore must have 2 columns. And it works. To multiply a matrix by a vector, or to multiply 2 matrices together, we use the R operator %*%. Let me introduce a matrix V whose elements are 1 and 3. And now let me calculate a matrix W that results from multiplying the matrix A by the vector V. Here's how the answer comes out. To get the top entry in the matrix W, in the vector W, which is a 5, I go across the top row of the matrix A and down the vector V. 2 times 1 plus 1 times 3 equals 5. For the bottom entry, similarly, 4 times 1 plus 5 times 3 equals 19. Because we're really thinking of V as a column vector here, I use the as.matrix function to force it to display as a column. If I ask, what are these things? R tells me, well, W is not a vector. It's a matrix. No problem. I can add to W a vector with a pair of 5s. I get the right answer, but it continues to display as a column. If for any reason I ever need to turn it back into a vector, I use the R function as.vector. Before we can do matrix multiplication, we have to create a second matrix. So let's make a matrix B out of its two columns, and then ask R to multiply A times B and B times A. Different answers in the two cases. This is an instance of a mathematical operation that does not satisfy the commutative law. It does, however, satisfy the associative law. To check associativity, we need yet a third matrix, C. There it is at the lower left-hand corner. And now I can try doing the multiplication in three different ways. First, multiply A by B, then multiply on the right by C, or first on the right multiply B by C, then multiply on the left by A, or just do the whole business without any parentheses. And in every case, the answer is the same 2 by 2 matrix. One of your proofs will be to show that this is true by using the rule for matrix multiplication. Another way of proving this is to learn that matrix multiplication represents composition of functions, which is always associative. We can add matrices together, provided they have the same shape, just by using the plus operator. The reason this works is that as far as R is concerned, a matrix is just a special type of vector, and the plus sign adds vectors together. Matrix multiplication and addition satisfy the usual distributive law. I check that by doing the addition first and multiplying by C on the left, by doing the matrix multiplication first and then adding the results together on the right, and I get the same answer in both cases. In the case of fields, a single distributive law is all we need because multiplication is commutative. In the case of matrix multiplication, which is not commutative, we need to state explicitly a second distributive law, saying that if we do the addition on the right, the operation is still distributive. Sometimes you want to extract pieces of a matrix. In the textbook, the entry in row I, column J is represented by A subscripted by I, comma J, and R uses exactly the same notation. Since the column index comes second, if you want the first column of matrix A, you ask for A square bracket, comma 1. Since the row index comes first, if you want the second row, you use A square bracket 2, comma. If you want the entry in row 2, column 1, you use a pair of indices, A square bracket 2, comma 1. What you almost certainly don't want to do is say A square bracket 4. R won't complain about this because it thinks a matrix is just a kind of vector. I will find the fourth component of that vector. But using a matrix with a single subscript is almost always a very bad idea. Another useful matrix operation is to take the transpose. The transpose function is represented by little t, and if I look at little t acting on A, you see all I have done is to make the columns of A into the rows of the transpose. I can also evaluate the determinant. You probably learned in high school that the determinant of this 2 by 2 matrix is 2 times 5 going down the main diagonal minus 4 times 1 going along the off diagonal, and the answer comes out to be 6. Finally, I can calculate the inverse of the matrix using the function named solve. So when I say M gets assigned solve of A, there's the answer. And to check that I really have got the inverse, I multiply M by A. I also multiply A by M just to confirm that this is a two-sided index. In two-sided inverse, it works in either order. Now it's a little bit annoying seeing 5.55 times e to the minus 17th. Most people regard that as equivalent to 0. And if you want things to look prettier, you can use the round function to round everything off to 6 digits. In the executive summary is the rule for inverting a 2 by 2 matrix. This is the only case where you can do it by inspection. And the rule says, given this matrix T, what I do is swap the entries 3 and 2 on the main diagonal while negating the entries 4 and 1 on the off diagonal, and then I divide by the determinant. If I do that in R, here is the result. And when I multiply that inverse by my original matrix T, I get back the identity matrix. Here's an operation that does something you probably didn't want to do. Ordinarily, in R, caret 2 squares something. So if I ask R for 3 caret 2, it will give me 9. But if I ask it to square A, it will say, oh, A is a vector. He wants the squaring operation applied to each entry. And what I will get is a matrix that has in each position the square of the corresponding entry of A. That's not what I want. What we refer to as A squared is A matrix multiplied by A, and there's the right answer. Now let me show you how we can solve equations using matrices. Here's a pair of equations. Takes you back to those middle school days. 4x plus y equals 11, 2x minus y equals 1. We can make the left-hand side into a 2 by 2 matrix by binding the two rows together. We can make the right-hand side into a column vector. And now in R, the function solve with 2 arguments will solve the equation matrix S multiplied by vector V equals vector W and give us the matrix V. To confirm that this is correct, we just multiply S by V and we get back W. Now let's look into something a little bit less mechanical, namely the relationship between linear functions and matrices. Here is a function whose name is little f, which is a linear function. It takes a single argument, a vector, and it works by multiplying the first component of that vector by the vector 1, 2, and the second component of the vector by the vector minus 3, 1. I can confirm that this is really a linear function by trying it out on a linear combination of vectors. I've defined 2 vectors, v1 and v2, and 2 coefficients, a1 and a2. I apply f to a1 times v1 plus a2 times v2. If f is linear, the result should be the same as a1 times f of v1 plus a2 times f of v2, and sure enough it is. So how will we construct the matrix that represents a linear function f? Easy. The first column is f acting on the first standard basis vector, 1, 0. The second column is f acting on the second standard basis vector. So from our linear function little f, we've succeeded in creating the matrix capital F that represents it. And now, having created that matrix, we can use matrix multiplication to evaluate the function. Given the vector x, whose components are 2 and 3, I can either let the function little f act on x, giving me minus 7, 7, or I can let the matrix capital F be multiplied by x. Again, I get minus 7, 7, though R likes to display it as a column. Now the meaning of matrix multiplication becomes apparent. It represents composition of linear functions. Here is a second linear function, which I've constructed in a similar manner to f and given the name g. And I can make the matrix that represents it by letting it act on the first and second standard basis vectors and pasting the two columns together to make the matrix G. I will use the name fg for the composition of the two functions. That's just f of g of v. So now we've defined the composition function. And we can, in the usual way, construct the matrix that represents it. Remarkably, I can get exactly the same result by forming the matrix product of f and g. So far all our matrices have been square, but matrices don't have to be square. Here is a 3 by 2 matrix. That means 3 rows, 2 columns. It has 6 entries, and the second argument to the matrix function says it has 3 rows. Here's M23. This has 6 entries, but now it has 2 rows and 3 columns. I can't add these matrices together because they have different shapes, and R tells me I have made an error. I can multiply the matrices together if the number of columns in the right-hand factor equals the number of rows in the left-hand factor. If I take M23 and multiply it by M32, I get a perfectly good 2 by 2 matrix. If I try multiplying M32, which has 3 rows and 2 columns, by M32, which has 3 rows, R will complain. Finally, a few things about the determinant. R regards the determinant as a function of a square matrix. But if we make the matrix by binding together 2 columns, each of which is a vector, then it might be useful to think of this determinant as a function of the 2 columns. A convenient way to do that is to define our own function, call it det2. This is a function of 2 vectors, the first column and the second column, and the definition is just bind them together to make a matrix, then calculate the determinant of that matrix, and we get exactly the same answer. Viewed as a function of its 2 columns, the determinant has 3 properties which generalize from 2 by 2 determinants to n by n determinants. First property, if you swap the columns, interchanging v1 and v2, the determinant changes sign. It goes from 2 to -2. Second, if you fix the second argument, specify the second column is permanently v2, then this matrix is a linear function of the first column. I can evaluate it with the first column of v1 plus 2 times v3, compare with what happens when I add together the results of evaluating it with the first column v1 and adding on twice the determinant where the second column is v3. And finally, if the columns are the standard basis vectors in order, the determinant comes out to have the value 1. You will learn next week that this same set of properties holds for 3 by 3 matrices, and in the spring term you'll learn that these 3 properties actually define the determinant of an n by n matrix. Sometimes you want to know whether 2 vectors are proportional. Because the determinant of a matrix with 2 proportional columns is always 0, an easy way to check for 2 vectors being proportional, or to use a fancier term, linearly dependent, is just to evaluate the determinant function on those 2 columns. Finally, the determinant has an interesting geometrical significance, and now we can draw a pretty diagram to represent this. First, we will make a matrix M and calculate its determinant, that happens to be 4. Then we'll set up a screen with the narrowest possible margins and an aspect ratio 1. If you look at the plot function, you'll see I specified ASP equals 1. That means 1 unit along the x-axis equals 1 unit along the y-axis, and a square will actually display as a square. Let's first display the two standard basis vectors. There's the first standard basis vector and what happens to it when we apply the matrix M. The second standard basis vector and what happens to it when we apply the matrix M to get a vector V2. Out of the columns of the matrix M, I can make a nice parallelogram shown in red. Out of the standard basis vectors, I can make a nice square displayed in green. The red parallelogram has exactly 4 times the area of the green square, and that's the geometrical significance of the magnitude of the determinant of a 2 by 2 matrix. It's the area stretching factor. One of your homework problems will involve exploring what's the significance of having a positive value of the determinant and what's the significance of having a negative value for the determinant. Now you're pretty much ready to start doing things with matrices, and so that ends this introductory script.